So we're going to begin with a review of logistic regression, in particular, the case study of binomial ordering preferences. Binomials are expressions of the form x and y, where x and y are each a single word. And we saw a variety of types of pairs where you had varying intuitions about what the preferred order was. So here are a few examples we looked at. So for example, in the case of pepper and salt versus salt and pepper, people had the very strong intuition that salt and pepper was a preferable ordering. In cases like deer and trees, you had perhaps not quite as strong an intuition, but you probably felt that that was a little bit more natural than the alternative ordering, trees and deer. Now, both of those cases and a lot of other ones that we're seeing here below are cases where these are what are called attested binomials. They're ones that you have direct experience with in your lifetime, most likely. And in general, it's the case that you also prefer the ordering in which they occur. Most often. So you probably are doing some learning of that from your experience in the everyday linguistic environment. Of course, not in all cases will there be a strong ordering preference in either direction. So for example, in the cases of skirts and sweaters versus sweaters and skirts, we saw that these two were fairly equally preferred. People generally didn't have very strong preferences between the two. But I also want to point out, and you may remember this, that even for cases where you've never heard the expression in either order, you can have strong preferences. So for example, for bishops and seamstresses versus seamstresses and bishops, most people tend to find that bishops and seamstresses is a more natural sounding order than seamstresses and bishops. And this is because of the fact that these ordering preferences are being guided not only by your direct experience, but also with productive preferences. And sometimes in linguistics, these are talked about as constraints. And there are constraints that guide whether one or the other form is preferred, but they can also be cross-cutting. Sometimes they don't always go in the same direction. So here is a review of the major constraints that we looked at. 4 of these are about the semantics of the words. So the most powerful one is iconic or scalar sequencing. What comes first sort of meaningfully is said first. So for example, you open and read a book, you don't read and open it. Perceptual markedness is like more animate, more positive things tend to come before less animate, less positive things. So for example, deer is more animate than trees, so deer and trees is preferred over tree and deer. Formal markedness, more general meanings come before more specific meanings. So for the case of change and improve, improving is a kind of changing. And so people tend to say this more general thing and then the specific thing after that. Power, what's socially more central or more powerful tends to come first. So in a meal, food and drink, food is the central thing, drink is sort of the side thing, so you generally say food and drink, not drink and food. There are also non-semantic constraints. So for example, these two are about the phonological form, the sound form of the word. So in confuse and disorient, confuse ends with a final syllable stress, fuse, whereas disorient doesn't. This final syllable is not stressed. And generally it seems that people don't like to choose orderings that put final stress on the entire phrase. So confuse and disorient is preferred over disorient and confuse. And short before long is a very important one that's easier to notice. Short words tend to come before long words. So cruel and unusual. Cruel is a shorter word than unusual. It's 1 syllable versus 3 syllables, and that's the preferred ordering. And then this constraint is one that maybe we want to think of neither as about phonology nor semantics, but it's about the lexical properties of the word above and beyond that. So in particular, for neatly and sweetly, these are both bisyllabic words. They're both words of similar similar semantic specificity, but neatly is a more frequent word than sweetly. And neatly and sweetly, in fact, is preferred over sweetly and neatly. So that's the 7 constraints that we've looked at before. And I've quantified them roughly in terms of their ordering power, their power. The iconicity constraint is by far the strongest. The other semantics constraints are relatively strong. The phonological and lexical constraints are a little weaker. And so larger strength means means more strong guidance toward ordering preferences. But how do we formalize that notion of strength? And in our case, we use logistic regression to do this. So logistic regression, to remind you, says that we want to think of each of these constraints and whether a particular ordered binomial satisfies or violates the constraints as something that we might call a predictor. And we'll call those predictors x1 through xn. And the formal commitment of logistic regression is that some notion of the preference for one outcome over the other, an outcome being a particular ordering that's chosen, is expressible as a weighted combination of the constraints or of the predictors. So here the betas are those constraint weights. So if we cache this out a little bit more, so we'll call these 7 constraints the x sub i's. They have values with respect to any particular ordered binomial expression, and the beta sub i's are the weights of the different constraints. And so these values, 20 through 0.3, are multipliers that would go in through the values of these constraints. And we'll get back to what the x values should be in a moment. Once those are combined, we wind up with a goodness score. That's often called eta in the logistic regression literature. And we convert that goodness score to a probabilistic prediction about which ordering is likely to be preferred by passing it through this, what's called the logistic activation or sometimes sigmoid activation function. So we say that the probability of quote unquote success, and we'll get back to what success is in a minute, is determined by this transform of the linear predictor. And so that winds up being the predicted mean, the predicted proportion of binomials with that linear predictor that will be chosen that order. This is the logistic or sigmoid transform activation function. It converts linear predictor values, which can range from negative infinity to infinity, to probabilities between 0 and 1. Now, I'm sorry, I should clear out those annotations for a moment. So let me just give a simple example of how this looks in a 2-constraint setting. We'll use the 2 constraints of word length and word frequency. So let's look at some examples like this. First of all, we'll go we'll go look at the equation. So if it's a 2-constraint model, there are 2 predictors, a number of syllable predictor for word length, and a frequency predictor for word frequency. And the linear combination of that, where the betas express the weights of the constraints, will determine the linear predictor. And then that will be transformed into a probability of quote unquote success. At this point, we need to say what success is. So reminder, this is the logistic sigmoid activation function. We're going to arbitrarily define success as the choice of the alphabetical ordering of the constraint. And actually, it really will not matter the way that we're setting this up, what we happen to choose as success. We just have to conventionalize that for any 2-word pair, we have to choose one ordering as what counts as a successful ordering and the other as a non-success ordering. And so basically, it's determining which side of a coin that is weighted, which sort of is the probability of the choice of the ordering for the binomial, which side counts as heads and which side counts as tails, so forth. So here are some examples of this. So, and what I've done conventionally is I've chosen 6 binomials that actually occur in naturalistic text, and I've shown you the alphabetical ordering of them. And I've shown you whether they indicated here in this table, whether they satisfy or violate or are sort of invisible to the constraint in question. So let's start with calm and relaxed. So calm and relaxed is calm as a monosyllabic word, relaxed is a bisyllabic word. That ordering then satisfies the short before long constraint, so we'll give it a green check mark. Calm is actually a higher frequency word than relaxed, so it also satisfies frequent before infrequent, so we'll give that a green check mark. In contrast, if we take big and thick is 2 monosyllabic words. And so whether you choose that ordering or not, the short before long preference would be the same. So this constraint is in a sense inapplicable to this ordered binomial. On the other hand, big is a higher frequency word than thick. So big and thick ordering satisfies frequent before infrequent. If we had chosen the thick and big ordering, then we would have NA here and we would have an X mark here. And here are these other examples just to draw your attention. So there really are examples that violate multiple constraints in naturalistic text. So for example, crochet and knit. Crochet is a bisyllabic word preceding a monosyllabic word, so it gets an X in short before long. And knit is also a higher frequency word than crochet, and so it gets an X in frequent before infrequent. Now, we're still not done, because we actually have to convert these check marks, X's and NAs, into values that will feed into the X's. And we're going to do this by a numeric coding of each possible constraint satisfaction value into a number. So for the syllabic, the XSIL constraint, we'll say that a green check mark is a +1, a red X is a -1, and NA is 0. What's crucial here is that the NA values are 0 and that these two values are equal and opposite. And what that will mean is that the choice of which counts as the quote-unquote success ordering for the binomial will not affect the model's predictions or the fitted values that you get for the model. For frequent before infrequent, it's a little simpler because there's no NA, and you would get these plus and minus ones. So at this point, we can now actually fit and use a fitted logistic regression model to make predictions about binomial ordering preferences.